Hi, welcome to the first episode of Proof Pilot. We are here to talk about real numbers. What are they? Well, to understand what a real number is, first we need to go further back and remember what the first set we learned in school. Well, can you recall that? Yes, that's the set of positive natural numbers 1, 2, 3, and so on. What you can do with natural numbers, positive natural numbers, is you can define addition on them. Like you take two numbers and then add them together, and it gives you a new number which belongs to your set. But can you do the same with subtraction? Like, can you take two number and then just subtract them? Well, obviously you can't because, for example, take 1 and 2, you get 1 minus 2, and that would be minus 1, which does not belong to our set. So to solve this problem, what you did was you learned about negative numbers and you already knew about 0, and you just poured all of those numbers in one set. We named it set Z, which we called it set of integers. So now what you can do is you can define subtraction with these numbers and you won't have a problem. But what about division? Can we do the same with division? I mean, obviously we can't do division with integers because, well, they wouldn't be defined like the way subtraction wasn't defined in the set of natural numbers. Like 1 over 2 doesn't mean anything in the set of integers. So we expanded the set of integers to the set of rational numbers, and now we can do division. I mean, it's a bit complicated process, but you can find that on algebra books. Now we can get back to our question that what's a real number? Well, first of all, let's take a look at Q. I mean, why do we even need a real number? Maybe Q is complete and everything we need is in Q. But there's an easy example for that Q is not complete. And that easy example is square root of 2, which we already know exists because it's simply the diagonal of a square with the length of 1. By Pythagoras' theorem, this would be square root of 2. But do we really know that the square root of 2 is not a rational number? I mean, who told you that? Maybe it's a rational number. Our next step is going to be to prove that square root of 2 is not a rational number. That will be our first theorem. Now we are going to prove this theorem to understand that there are some points that does not belong in the set of rational numbers, and the way mathematicians call that is that Q is not a complete metric space. Let's prove this theorem right here. The way we are going to prove that is by contradiction. Let's assume that square root of 2 is a rational number, and we take P and Q to be relatively prime to each other, so their greatest common denominator would be 1. Let's take this equation right here and write it again. Let's take both sides of the equation to the power of 2, and we get p squared over q squared, and then just take the q to the other side we get 2q squared equals to p squared. And that equation right here is gonna solve all of our problems. Now let's do a case-by-case scenario. The first case is that p is an odd number. If p is an odd number, then p is a representation like this. And if we take both sides to the power of 2, we get p squared equals to 2k plus 1 squared, and that is equal to 4k squared plus 4k plus 1. And odd number because if you factor the 2 in this polynomial right here, you get 2k squared plus 2k, and just leave the 1 right here alone, and like you can name this z right here, and you get 2z plus 1. So that's a odd number. But right here we can see that p squared is an even number because it is equal to 2q squared. So that will be a contradiction. So that's our first case. Now we get to case 2, which is obviously p is an even number. Well, if p is an even number, then p squared must have even number of times of 2 in its factorization. So from p squared equals to 2q squared, this means that q squared must be even. So q squared is even, and if q squared is even, so is q. P is also an even number, and we already knew that the greatest common denominator of these two will be 1, but they are both even, so this is going to be 2, which is a contradiction right here. And now we are done with this theorem. So now that we know that the square root of 2 does not belong in the set of rational numbers, so what is the square root of 2? Well, Richard Dedekind in 1876, if I recall correctly, gave us a definition for what a real number is. First, he gave us the definition to what a cut is. So let me just write that definition down. Okay, Richard Dedekind gave us a definition about what a cut is. So he defined that a cut in Q is a pair of subsets A and B of Q such that it has three properties. A union B equals to set of rational numbers, and A and B, they both aren't the empty set, and the intersection of A and B is equal to the empty set. They do not have any intersection. The next one is if you take a member from A and a member from B, then the member from A is definitely smaller than the member from B. And the third property says that A contains no largest element. And this is the definition that Dedekind gave us to define what a real number is, and that is really simple. And he just simply defined that a real number is a cut in Q. And if x is a real number, we show it like this: a cut b, if a and b are set in our cut. And if you're having problems imagining what a cut is, just imagine you are cutting through a line, and where you are cutting exactly will be your cut. And what we are saying that what a real number is, the left side will be a and the right side will be b. Okay, now we know that what a real number is, but this may occur to you that a real number is now like this. It looks like this, which a and b are sets. So if, for example, I have another real number like c cut d, then what's the answer of x plus y? I mean, they're both sets. What's this? So we actually have to define all of the other things that we knew in a metric space, like rational numbers in in this metric space. We have to define it all over. Like, what does it mean? Like, x is smaller than y, or x is greater or equal to y. We have to define all of this again so we can work with this metric system. So I'm gonna write what's the definition of x plus y, and you actually have to go through all of those things that are needed for this thing we defined right here to be a metric space. I mean, to be a field, because the set of real numbers is a field. So I'm not gonna go through that, but I'm just gonna write here what this operation is defined with this definition that we just gave. Okay, here what's the answer of this right here, x plus y, with this definition. Uh, it certainly is another cut, and the way we define it is like this. For some a in a and some c in c, r equals to a plus c, and just all pour all those into e, and your set d will be the rest of q. So the answer to x plus y is e cut f with this definition right here. And we are done. Now you know what a real number is by the definition of Dedekind cuts. But have you thought that maybe this r right here isn't complete itself? Like, we just said that q has holes in it. Okay, the holes were the set of the holes were irrationals and numbers like square root of 2. But do you think that there is a hole in set of real numbers? Like, is it possible? I mean, what is even the definition of completeness? I mean, what's the mathematical definition of completeness? And that is what we are going to talk about in our next video. I hope you have enjoyed this one. Thanks for watching.